Hello viewers, in my previous lecture I had discussed with you interconversions of monosaccharides, that is conversion of glucose to fructose and fructose to glucose, that is conversion of aldoses to ketoses and vice versa. And the series of reactions which we use there can be used for conversions of all aldoses to ketoses. Then we discussed that how will we convert a lower aldose into a higher aldose. Say for example, we are converting arabinose, D-arabinose into D-glucose and D-mannose. So in that case, we will bring about the reaction by Killiani-Fischer synthesis. And the vice versa reaction, that is when we are going from higher aldose to a lower aldose, we can use roof degradation. In my previous lectures, I have also discussed with you the properties of glucose and fructose, and I have also discussed with you structure of glucose, the brief structure as to how can we represent a molecule of glucose. Now in today's lecture, I shall be discussing with you the structure of glucose in detail, right? And let us see how will we do that. So when we talk of structure of glucose, you already know that structure of glucose can be represented in one of the following ways, and which you can see on your screens. The first representation is that of Fischer formula. That is, how did Fischer said represent the molecule of glucose? He said that we will take the longest carbon chain as the parent chain with the highest oxidized end at the top, and the vertical lines represent the bonds which are going away from the observer, and horizontal lines represent the bonds which are coming towards the observer. Then he went on to represent this structure into Haworth structure, and in Haworth structure what we find that the bonds which are on the right hand side will go below the ring, and the groups which are on the right hand side will go below the ring, and which are on the left hand side will go above the ring. Next point, what we find is the better representation of Haworth is that we can represent it in the conformation form, that is we represent it in the non-planar form. So what happens is that when we talk of the Fischer projection formula, we find that it is able to explain many properties of glucose. That is, it is able to explain the property of an aldehyde group, that glucose has an aldehyde group, then glucose has 5 hydroxyl groups, and it also represents that glucose is a straight chain molecule. But it was not able to explain some of the other properties of glucose, like the phenomena of mutarotation, and why does glucose not react with sodium bisulfite, and why does it not react with Schiff's reagent. So another structure was proposed for it, that was the cyclic structure, and this cyclic structure now represented the properties of glucose. So what we find, how do we get this cyclic structure? That one of the hydroxyl groups here on C5 reacts with an aldehyde group to give us a hemiacetal structure, and in which the OH is on the right hand side here, which is inside the ring. Please remember that is the structure of alpha D glucose, and this is not correctly represented here. If this OH was on the left hand side, that is OH is here. This is the anomeric carbon that we are representing. I repeat, this is where we are, this is on the basis of the position of these OH, we will find out which is the alpha and which is the beta. So this is the alpha form in which OH is on the right hand side, and this is the beta form where the OH is on the left hand side. So these cyclic structures can now be represented in two ways. We can represent it in a form of Haworth formula, and when we talk in terms of Haworth formula, we find that when we are talking of a 6-membered ring, the basic structure in 6-membered ring which is found in glucose is that of a pyrene ring. Therefore, aldoses which have, or ketoses which have 6-membered rings in them, they are known as pyranos. Pyrane, that means the basic structure here is that of pyrene ring, and O since it is a carbohydrate. But if the ring is 5-membered, as we've seen in our previous lecture in case of fructose, then what we find that there the basic structure is that of furane, which is a heterocyclic oxygen compound, and therefore that ring which is 5-membered ring, we call it as furanose, because it has a basic structure of furane and then it is a carbohydrate, we call it as O's. So when we talk of Hayward formula, we will see that a ring can be monosaccharide will either be represented in a 6-membered ring or a 5-membered ring. Here I have shown 6-membered rings of glucose, and these are the pyranose rings, and as I have already said that the groups which are on the right hand side will go below the ring and one which are on the left hand side will go above the ring. And this you have to remember is the anomeric carbon, that is the aldehydic carbon in the open chain structure, which is being converted into a new asymmetric carbon when we are talking of a cyclic structure. Now next we go on to how can we represent this cyclic structure. It can be represented in chair conformation. We prefer to represent the Hayward projection in chair conformation, which is a 3-dimensional configuration of a sugar in nature. And why do we like to do this? Because we know that the 6-membered rings are non-planar, and especially the chair form is non-planar, and it is stable, because in that case all the bond angles are 108 degrees, which should be the bond angle of a sp3 hybridized carbon. So what we find that this Hayward projection or the sugar molecules are prefer to occur in the chair conformation, and we know that why so, because the 6-membered rings like cyclohexane are the most stable conformations. So here we have a structure for glucopyranose, that is the alpha D glucopyranose, and here we have a structure for beta D glucopyranose. I would like to specify 2 things here. Alpha means that here the OH is at the anomeric carbon is at the axial position, and here it is at the, in beta form it is at the equatorial position. Right, and the second thing that you have to remember is D. What does this D indicate? This D indicates that the OH, when we are talking of the open chain structure, the OH at the highest numbered asymmetric carbon is on the right hand side. Then of course you know that the small d, this plus or small d would indicate that the molecule of glucose is what? It is dextrorotatory. Then gluco, that is it is the cyclic structure, the pyranose structure of glucose, and similarly it is again the pyranose structure, but this is having beta form and this is the alpha form. So after introducing you to the basic structures of glucose, now we have to go on to how was the open chain structure of glucose elucidated. How do we come to the conclusion that glucose has 1 aldehydic group, 5 hydroxyl groups, and it is an open chain structure? So the first thing that we are going to do when we are elucidating the structure of a particular molecule, which could be glucose or which could be fructose, we are going to do elementary analysis. This elementary analysis will help us in finding out the number of each type of atoms in it. Right. Then we will go on to establish, okay fine, we've got this molecular formula. How are these groups or how are these atoms arranged in a molecule? And ultimately we will go on to, we know that this glucose has 4 chiral carbons in it, glucose molecule. So what is the configuration around each chiral carbon? We have to establish that, and this was a very, very tedious job, believe it or not. Because at that time when Fisher worked with the structure of glucose, no X-ray, no spectroscopy techniques were available, no modern techniques were available. So he had to work with whatever data which was available to him then. So now, as I said, this will involve 3 steps. Let us see what does elementary analysis involve. Elementary analysis involves detection of elements. First of all, we are going to find out what are the elements present in glucose. And then we have to find out what is the percentage of each element, that is carbon, hydrogen and oxygen in glucose. And then we will derive from that percentage, we'll derive the empirical formula of the molecule. And after we know the empirical formula of the molecule, we will find out the empirical formula weight, and we know the molecular formula weight. And after determining the molecular formula weight, we will divide the molecular formula weight with the empirical formula weight. From there, we'll get a value of n. And then when we get the value of n, we will multiply the empirical formula by that n. That value, it could be 2. So if it is supposing 2 and the empirical formula was CH2C, CH2O or C, so what will we do? We will, whatever the empirical formula would be, we will multiply that by 6. So if I say it was CH2O, so when we multiply it by 6, what do we find? That we'll multiply everything by 6. So carbon will become 6, hydrogen will become 12, oxygen will become 6. So first aim is going to be to establish the molecular formula of the chain. After establishing the molecular formula, now we have to establish that glucose has 1 aldehyde group, it has 5 hydroxyl groups, and it is a straight chain compound. And this work was done by Baer in 1870. And he did the following reactions. He carried out the following reactions, which you can see on your screens now. But we've already discussed these reactions in detail, so I will be quickly going through these reactions. So in the first case, to prove that the glucose has an aldehyde group, it has a carbonyl group, and which is an aldehyde group. So the following set of reactions were carried out. And they knew that this is what experimentally, when they treated glucose with these reagents, they found they were giving us these reactions. So when a molecule of glucose was treated with HCN, we got a cyanohydrin. And we know that these are the reactions of a carbonyl group, because we know that whether a molecule has an aldehyde group or it has a ketonic group, it reacts with HCN to give a cyanohydrin. And what is a cyanohydrin? In which a CN and OH are attached to the same carbon atoms. And here you can also observe that in the process, a new chiral carbon is generated, and there is also lengthening of the chain. But nevertheless, this reaction proved that it has a carbonyl group. Next, glucose was treated with hydroxylamine. And when it was treated with hydroxylamine, it underwent condensation reaction, in which oxygen of the aldehyde group and H2 from hydroxylamine was eliminated as water molecule, resulting in the formation of glucose monooxime. This again proves that this molecule has a carbonyl group in it. And then the next reaction was carried out with phenylhydrazine. And when the reaction was carried out with phenylhydrazine, they got ozazone. And you know, when you're carrying out the reaction with ozazone, it is only the first two carbons which are involved in the reaction, right? So what happens? That means now these people knew that the group is again a carbonyl group here, and this is the structure of D-glucose. That is, this was D-glucose, and it has the carbonyl group. And you know that when we talk of a ketohexose or any ketose, it reacts with phenylhydrazine to give us the same ozazone as an aldose would do. So that means that again we are proving that it has a carbonyl group. Now what was done was that they wanted to prove that this group is again a reaction was aldehyde group, And when they carried out the reaction with Benedict's reagent, which is sodium potassium tartarate and copper sulfate, they got a red precipitate of cuprous oxide, and this CHO was oxidized to COOH group. This reaction again is given by the reaction of a carbonyl group, that is an aldehyde, that is glucose as well as fructose will give this reaction. So now they had to specifically say that this is a this group, that is the carbonylic group, is the aldehydic group. But now when they carried out the reaction with bromine water, what they found that this group is being oxidized to a carboxylic group. If we were carrying out the reaction of a ketose with a bromine water, it would not give us a gluconic acid, or it would not give us aldonic acid, because the ketonic group is in the center. There the bond cleavage would take place and we would get a mixture of acids, whereas in this case you were getting gluconic acid. So this specifically proved that the carbonyl group in glucose is the aldehydic group. So the first four reactions showed us that the glucose has a carbonyl group. But when we carry out the reaction with bromine water, it tells us that the color of the bromine water is discharged, and then what we find that we get a monocarboxylic acid, which is D-gluconic acid, which proves that this carbonyl group is an aldehydic group. So glucose has an aldehydic group. It is not a ketonic group, because if it were a ketonic group, the molecule would have cleaved and we would have got a mixture of two acids. And then when we carry out the reaction with nitric acid, which is a strong oxidizing agent, it would again oxidize the the aldehydic group as well as the primary alcoholic group. And what we'll get a dicarboxylic acid here, which is glucaric acid, and this again proves that this molecule has one aldehydic group, and among the 5 hydroxyl groups, one of the hydroxyl groups is primary. And the second case was that when the reduction was carried out of this molecule, so what happened was that we got a hexahydric acid, only one hexahydric acid, that is sorbitol. If by chance the group would have been ketonic, we would have got a mixture of sorbitol and mannitol. But here we are getting only one form. So we say that this is again, it proves that this group is an aldehydic group. So now we've proved with the help of reactions that glucose has an aldehydic, it has a carbonyl group, and then by carrying out the reaction with bromine water and reduction, we have proved that this ketonic group, this carbonyl group is an aldehydic group, and this aldehydic group is present at carbon number 1, because on oxidation we are getting a dicarboxylic acid, the bond is not being cleaved. So that means now we've established that with the help of reactions that in glucose we have an aldehydic group, and we have a hydroxyl group which is a primary hydroxyl group. Now we have to prove that glucose has 5 hydroxyl groups. So what was done, this glucose was treated with acetic anhydride in presence of zinc chloride. So when it was treated with acetic anhydride in presence of zinc chloride, this is an esterification reaction. And what happens in esterification is that this bond between O and H will cleave, and we'll get a CH3CO from here, and we will get a pentacetate. The function of zinc chloride is that zinc chloride will make a bond, will coordinate with oxygen, and it will help in the cleavage of OH bond. So when the reaction of glucose was carried out with acetic anhydride in presence of zinc chloride, a pentaacetate was being formed. So when a pentaacetate is being formed, this clearly indicated that glucose has 5 hydroxyl groups, and this D-glucose pentaacetate is stable. So when it is stable, this also clearly then indicates that the 5 hydroxyl groups are attached on different carbon atoms. They are not attached to the same carbon atoms. If they were attached to the same carbon atoms, we would not get a pentaacetate. Then the next reaction which was carried out, that is the glucose was converted into penta-O-methyl D-glucose. That is, it was converted into ether. So the reaction was again carried out with dimethyl sulfate in presence of sodium hydroxide, and all the hydroxyl groups which were present, the 4 hydroxyl groups which were present here, were converted into the ether group. The ether 5, we got a ether group. That is, we got penta-O-methyl O-glucose. So this again proves that the 5 hydroxyl groups are attached to different carbon atoms. Right? If they were attached to the same carbon atoms, the molecule would not have been stable, because we know if 2 hydroxyl groups are attached to the same carbon, the molecule is unstable and it has a tendency to lose a water molecule. So these reactions proved that the glucose has 5 hydroxyl groups which are attached to 5 different atoms, and the molecule is stable. Now the next they had to prove was that Bayer had to prove that these glucose the carbon atoms in glucose were arranged in a straight chain. So how was this done? So what was observed, that when glucose was reduced with HI and red phosphorus, it formed N-hexane, and we know that N-hexane is a straight chain molecule. That is, it is a alkane in which the 6 carbons are arranged in a straight chain. So this is what N indicates here. And what does D indicate here? That we are starting with the molecule which has glucose, which has D configuration. If it was a branched molecule, we would have got a substituent here. We would not have got a straight chain compound. So therefore, it proved that in glucose, the 6 carbon atoms are arranged in straight chain. Not only this, when glucose was treated with HCN, it formed a cyanohydrin, and then when we carried out its hydrolysis, and that after hydrolysis the reduction was carried out, N-heptanoic acid was formed. So this again proves that the 6 carbon atoms are in the straight chain. So what was done, that the reaction was carried out with HC, with the aldehyde group. So this proved that aldehyde group is at the 1 corner, which is the first carbon, and here we had a straight chain lengthening, and a cyanohydrin was formed. And then when the cyanohydrin was hydrolyzed in acidic medium, this CN was hydrolyzed to a carboxylic group. So that means from 6 carbons we are going on to 7 carbons. And then when this acid was reduced, and what was formed, that HI and on heating, all the hydroxyl groups were reduced and heptanoic acid was formed. That is, an acid having 1 carbon more were formed, and that also had that was also a straight chain compound. So this clearly indicated that the glucose molecule has 6 carbons in straight chain. So now let us see, on the basis of the observations of Bayer, what was the open chain structure of glucose. So the open chain structure of glucose indicates that glucose has 6 carbon atoms in a straight chain. It has an aldehyde group, and it has 5 hydroxyl groups. Out of these 5 hydroxyl groups, 1 is primary hydroxyl group and the 4 are the secondary hydroxyl groups. And these 4 carbons, 1, 2, 3, 4 carbons are the chiral carbons. So till now we have established the open chain structure of glucose. But now the objective is going to be what is the configuration at the each carbon when we are talking of the structure. So what we have to see that what is the configuration when I'm talking of this carbon, how are these OH and hydrogens arranged in the molecule. This we shall be discussing in our next lecture by discussing Fisher's proof for the structure of glucose. Thank you.